Welcome to another deep dive. Today, we'll be tackling multiverse set theory.
Multiverse set theory.
It sounds kind of like science fiction,
Yeah.
but it's actually a real area of mathematical research. And it's seriously mind-bending.
It is.
We're basing this deep dive on a paper by Jouko Väänänen called Multiverse Set Theory and Absolutely Undecidable Propositions.
Yes.
And it's really a fascinating paper. He kind of goes off the deep end
In a
good way.
Well, he really dives into the deep end with this idea of a multiverse of sets.
Yeah.
What I find fascinating is that this isn't just some theoretical idea.
Yeah.
Väänänen actually builds a rigorous framework for how this could work.
Right.
He starts with a problem that's been bugging mathematicians for ages. Those pesky undecidable propositions.
Yeah.
Like Gödel's incompleteness theorems or the continuum hypothesis.
Right.
You know, the ones that can't be proven or disproven within our usual set theory.
Right. And if those propositions can't be proven or disproven, what does that even mean for their truth?
Exactly.
Do they even have a determined truth value?
Yeah.
That's where things start to get really weird. Right?
Exactly. It makes you question the very nature of mathematical reality.
Yeah.
And Väänänen's proposal is a bold one. What if there's not just one mathematical universe, but a whole multiverse of them?
Okay.
Each universe might have its own version of set theory.
Right.
And maybe in some universes, the continuum hypothesis is true.
Okay.
And in others, it's false.
So instead of one ultimate mathematical truth, we might have a whole bunch of different truths.
Yes.
Each valid in its own universe. That almost feels like cheating.
Yeah.
Does that mean we can just make up whatever mathematical rules we want?
Not exactly. There's still rules even in a multiverse.
Okay.
The axioms we choose still define what kinds of universes are possible. It's more like we're exploring a vast landscape of possibilities. And each universe is like a different region in that landscape with its own unique features.
Okay, so how would these universes even be different?
Yeah.
I mean, we can barely wrap our heads around infinity.
Yeah.
And now we have to imagine a whole bunch of infinities.
Well, even something like the power set of the real numbers,
Right.
that's already incredibly difficult to conceptualize.
Yeah.
Maybe the power set operation itself isn't as clear-cut as we thought.
Okay.
It could be that it's inherently non-unique,
Right.
which would lead to different set theoretic universes,
Right.
each with its own distinct power sets.
I'm starting to see why this is so mind-bending.
Yeah.
So how do we even begin to work with a multiverse mathematically?
Väänänen uses the familiar axioms of Zermelo-Fraenkel set theory with the axiom of choice,
Okay.
or ZFC, but with a twist.
Okay.
In this multiverse context, the variables range over all universes simultaneously.
So these variables are like multiversal travelers,
That's a good way to put it.
existing in all these parallel realities at the same time.
Precisely.
Yeah.
But here's the catch. We can't isolate or name specific universes within the system.
Right.
They're all sort of blended together.
That makes sense, though, right? Because if mathematicians were always working within this multiverse,
Right.
they probably wouldn't even notice anything different.
Exactly.
The axioms and the way we use them would still be the same.
Yeah.
It's almost like we're all living in this grand mathematical structure,
Right.
encompassing multiple realities without even realizing it.
And that leads to the question, how do we talk about this multiverse mathematically?
Yeah. Okay.
We need a way to express relationships between those universes.
Right.
To talk about what's true in some and false in others.
Right.
And to even consider what might be the same across all universes.
Yeah.
That's where Väänänen introduces something really interesting.
Yeah.
A new kind of logic
Okay.
called multiverse dependence logic.
Okay.
Or MD.
Hold on. A whole new logic.
A whole new logic.
Okay, now I'm really intrigued. But I'm also going to need a bit of hand-holding here.
Sure.
What makes MD different from the logic we're used to?
Think about how we usually use logic.
Mm-hmm.
We assign values to variables, like saying x equals 2.
Right.
But in team semantics, instead of just one assignment, we deal with sets of assignments.
Okay.
It's like we're considering all possible scenarios at the same time.
Okay.
Kind of like looking at all the paths a choose-your-own-adventure book could take.
I see where you're going with this.
Yeah.
If we're dealing with multiple universes,
Right.
it makes sense that we'd need a logic that can handle multiple possibilities at once.
Exactly.
Mm-hmm.
And MD logic introduces some new logical operations that let us do just that.
Okay.
For example, there's something called the Boolean disjunction,
Okay.
which lets us say a statement is either true in the entire multiverse
Right.
or false in the entire multiverse.
So we're kind of forcing those tricky statements,
right.
those undecidable ones,
Exactly.
to pick a side, true or false. Even in a multiverse where things can be fuzzy, I like it.
Yeah.
It brings a bit of order to the chaos.
Right, and then we have the constant NE, which just means the multiverse isn't empty.
Yeah.
Sounds simple, but it allows us to build a more powerful statement. 6,
Okay.
which means a proposition is absolutely undecidable.
Okay.
True in some universes, false in others. It's like saying, we don't know the answer.
Right.
And that's okay, because it might be different in different universes.
So we could formally say that the continuum hypothesis is absolutely undecidable.
Yes.
True in some universes and false in others.
Exactly.
That's pretty cool. We're not just throwing up our hands and saying it's undecidable. We're actually incorporating the undecidability into our logic.
Precisely. But MD can do even more than that.
Yeah.
It can also help us find common ground between those universes.
Okay.
For example, we can use MD to assert that all universes have the same ordinals.
Right.
Those building blocks of infinite sets.
So even with all this multiversal craziness, there are still some things that are universally true.
Exactly. And there's a specific sentence in MD that essentially says the ordinals are non-well-founded, denoted by Fagenhoff. When we combine this with any first-order statement, we can actually make statements about the well-founded models of ZFC.
Okay, that's getting a bit complex, but it sounds like we're using MD to connect this wild idea of a multiverse back to our familiar, well-behaved models of set theory.
You got it. And this leads to a fascinating conclusion. You actually can't axiomatize the entirety of MD. It's inherently more expressive than traditional set theory. It's like it unlocks a whole new level of mathematical thinking.
So this MD logic is like our key to understanding this crazy multiverse.
Yeah.
It gives us the power to explore and describe it in ways that traditional logic just couldn't handle.
Exactly. And to bring it back to the idea of a generic multiverse, Väänänen actually demonstrates that we can capture the essence of Wooden and Steele's work within MD.
Now, hold on. Remind me about those generic multiverses. They were built through a process called forcing, right?
That's right. You start with a model of set theory and systematically extend it to create new ones. What Wooden and Steele found was that this forcing process creates a vast network of interconnected universes. And the amazing thing is, it doesn't matter which model you start with. You end up with the same multiverse.
Right. So even though we might be talking about all these different universes, they're not totally disconnected. There's some kind of underlying structure to the multiverse.
Yes, and that structure is something we can actually express using MD logic.
All right, you have to tell me more about this. How do we connect MD to these generic multiverses?
Väänänen introduces another new logical operation for this, which he calls GMV. It essentially encapsulates the key properties of a generic multiverse.
So by adding GMV to our set of axioms, we're saying, okay, from now on, we're working within a generic multiverse.
Precisely. We're choosing a specific kind of multiversal structure for our investigations.
I have to admit, this is all pretty mind-blowing. We've gone from questioning the truth of mathematical statements to imagining a whole multiverse of sets. And now we even have a logic that lets us work with this multiverse. It's a lot to take in.
It's a lot.
But it's also incredibly exciting.
I agree. And this is really just the beginning. There's so much more to explore in the multiverse of sets. And we'll delve deeper into those possibilities in part 2.
Okay, great. Welcome back to our deep dive into the multiverse of set theory. I'm still trying to wrap my head around everything we discussed in part 1. This concept of a multiverse is seriously challenging my understanding of math.
It's definitely a big jump from the traditional way of thinking about mathematics. But remember, Väänänen's framework isn't just about abstract mathematical structures. It has some pretty profound philosophical implications, too.
That's what I'm really curious about. What does the existence of a multiverse, even if it's just a hypothetical one, tell us about the nature of mathematical truth? Does it mean that everything is relative? That there's no absolute truth anymore?
That's a great question. And it really gets at the heart of what this multiverse idea is all about. It definitely challenges the traditional view of mathematical Platonism, which says there's one single, timeless realm of mathematical objects and truths that exists independently of us.
So instead of having one definite answer to a question like the continuum hypothesis, there could be multiple answers, each true in its own universe.
Exactly.
That's kind of unsettling, but also exciting in a way.
It suggests that mathematical truth might be more content-dependent than we thought. It doesn't mean that anything goes, though.
Right. I was just thinking, if truth is relative, couldn't we just make up any axioms we want and create whatever mathematical realities we like?
Yeah.
Wouldn't that lead to complete chaos?
That's a valid concern, and it's something that philosophers of mathematics are still grappling with. But remember, even in a multiverse framework, we're still operating within the bounds of logic and consistency. We can't just conjure up arbitrary universes out of thin air.
So there's still a framework.
Yeah.
A set of rules that govern what's possible even in a multiverse.
Precisely. The axioms we choose still matter. They determine the kinds of universes that can exist within the multiverse.
Right.
Think of it like this. The axioms are the rules of the game.
Okay.
And the universes are the different ways the game can play out.
I like that analogy. It makes this whole concept feel a bit more manageable. So it's like we're explorers setting out into a vast uncharted territory. We have some tools and maps to guide us. But there are still so many unknowns, so many possibilities waiting to be discovered.
That's a great way to think about it. And those discoveries might lead us to new mathematical concepts and tools that we can't even imagine right now.
You know, it makes me think about Laver's result that you mentioned earlier.
About being able to define the ground model, our original universe, even after we've created new ones through forcing.
Right.
It's like we can leave breadcrumbs as we journey through the multiverse so we can always find our way back home.
That's a really insightful observation. And it speaks to a deeper point about the interconnectedness of these universes, even though they might seem separate. Right. They're all related in subtle ways. They share a common origin, and they can influence each other through these forcing extensions.
Okay, but let's get down to brass tacks here.
Yeah.
Is there any way to know if we're actually living in a multiverse?
Sure.
Is there any empirical evidence for this?
Yeah.
Or is it purely a mathematical concept?
That's the million-dollar question, and unfortunately it's a tough one to answer. The multiverse, as we've been discussing it, is a mathematical construct. Testing it empirically is a whole other challenge, and it might even be impossible.
So we're kind of peering into a realm that's beyond the reach of our telescopes and microscopes. Exactly. But even though we might never be able to prove or disprove the existence of a multiverse in a scientific sense, the very act of considering it opens up new ways of thinking about mathematics and its relationship to reality. It forces us to question our assumptions.
Yeah.
And to consider possibilities that might seem strange at first.
Yeah.
But could ultimately lead us to a deeper understanding of the universe.
It's a reminder that even in a field as seemingly absolute as mathematics, there's always room for mystery, for uncertainty, and for the possibility of something truly mind-blowing just beyond our current grasp. I have to admit, it's a bit overwhelming to think about all the potential implications.
I understand. It's a lot to process, but remember, that's the nature of exploring uncharted territory.
Yeah.
We're bound to encounter challenges and uncertainties along the way. The key is to embrace those challenges and to keep asking questions.
You're right. The sense of discovery, the potential for breakthroughs that could revolutionize our understanding of mathematics, that's what makes it so exhilarating.
And that's what drives us as mathematicians, that insatiable curiosity to unravel the mysteries of the universe or perhaps the multiverse. We're constantly pushing the boundaries of what we think we know, searching for those deeper truths that might be hiding just beyond our current reach.
So for our listeners out there, what do you think? Does this idea of a multiverse of sets resonate with you? Does it challenge your preconceived notions about mathematics?
We encourage you to explore this concept further, to delve into the research and to form your own opinions. Don't be afraid to ask questions, to challenge the status quo, and to embrace the possibility that there might be more to mathematics and to reality itself than we currently understand.
Because ultimately, this multiverse of sets isn't just a mathematical concept. It's a reflection of our own intellectual curiosity and our willingness to push the boundaries of what we think we know. Stay tuned for part 3, where we'll wrap up our deep dive and leave you with some final provocative thoughts to ponder.
Welcome back to the final part of our deep dive into multiverse set theory. We've explored the mathematical framework, the philosophical implications, and now it's time to bring it all together and see what we can take away from this incredible journey.
What strikes me about Väänänen's work is that he doesn't just present the multiverse as a theoretical possibility. He gives us a way to actually work with it, to reason about it, using logic and mathematical tools.
That's what I find so fascinating about this whole idea. It's not just a philosophical flight of fancy. We have this new logic MD that lets us talk about the relationships between universes, about absolute undecidability, and even about the common ground that might exist between all these different mathematical realities.
And that's where things get really exciting. The multiverse view, combined with the tools of MD logic, opens up a whole new frontier of mathematical research. So it's not just about proving or disproving existing theorems, but about exploring completely new mathematical landscapes.
Exactly. We can ask questions that were simply unthinkable before. For example, what happens if we add specific axioms to our multiverse set theory? What if we assume that all universes have the same real numbers, but allow for different power sets?
Or what if some universes contain certain large cardinals while others don't? How would that affect the overall structure of the multiverse?
Those are fantastic questions. And the answers could lead to new insights not just about the foundations of mathematics, but about mathematics itself. We might discover new theorems, new concepts, even new branches of mathematics that we never knew existed.
It's like we've been given this incredible new toolbox and we're just starting to figure out what we can build with it.
It's important to remember that the implications of the multiverse view go beyond just mathematics. It has the potential to change the way we think about knowledge itself.
I'm curious to hear more about that. How could the multiverse change our understanding of knowledge?
Well, if there truly are multiple mathematical realities, each with its own set of truths, then it challenges the notion of absolute objective knowledge.
So instead of searching for one single ultimate truth, we might have to accept that there could be multiple valid perspectives, multiple ways of understanding the mathematical universe.
Exactly. And that shift in perspective could have implications far beyond mathematics. It could change how we approach other fields of knowledge, encouraging us to be more open to different perspectives and to recognize the possibility of multiple truths.
That's a powerful thought. It suggests that embracing the multiverse could lead to a more humble and nuanced understanding of the world around us.
I think so too. And it could also inspire greater creativity and innovation after all. If there are countless mathematical universes out there, each with its own unique properties, who knows what incredible discoveries await us.
It's as if we've been given a glimpse into a vast, interconnected web of possibilities. Now it's up to us to explore those possibilities, to push the boundaries of what we thought we knew, and to see where this journey takes us.
So as we wrap up this deep dive into multiverse set theory, we leave you with this final thought. If the multiverse is even a possibility, then it tells us something profound about the nature of mathematics and perhaps about the nature of reality itself.
It tells us there's always more to discover, more to understand, and more to wonder about. That's what makes mathematics and life itself so endlessly fascinating.
Thank you for joining us on this incredible exploration. We hope it sparked your curiosity and inspired you to continue exploring the multiverse of sets and the multiverse of ideas on your own.